Now we want to learn about extremal number of even cycle. So C2K. There are many proofs, several proofs showing that the extremal number of even cycle is some constant times n to the 1 plus 1 over k. And in general, we don't know whether this is tight, but for some cases it's known. Two, 3, 5, where k is 2, 3, 5. And you can notice that these are the small prime numbers. And you can guess that the construction that's showing lower bound here are algebraic, that uses some property of prime. So I want to prove this using the concept of graph homomorphism. So what do we have to do? So as we proved last time, if you know the average degree of graph G, then you can get the lower bound on the number of homomorphic copies of graphs in there. That's already, something that give you a homomorphic copy of this into K. However, we want to make sure that the third copy is not degenerate. So, if, you only have a degenerate copy, then what can you do? So we want to derive contradiction by assuming that essentially, okay, maybe let's introduce the, certain notation first and then discuss. So what's the homomorphic copy of C2K? That's exactly a crosswalk. Say P0, P1, P2K. And we said that this closed to K walk is degenerate, say at I, j, if Bi and Pj are fixed. Okay, so if you have this cycle, then that's the non-degenerate copy. But if you have a degenerate copy, it could be looking like this, or even like this. And here, it's not exclusive. So some copy could be degenerate at 1, 3, as rare as 1, 7, as rare as 5, 8. So for example, here 1, 2, 3, 4, 5, 6, 7, 8. Then it is 1, 8, 9, 10, 11, 12, 13, 14. And it could be 1, 2, 3, 7, and 14. So one homomorphic copy may be degenerate as several pairs of I, j. And we say that it is also, of I might say the absolute pair minus 1. So for example, if you have this degenerate copy, then this is of type what? Four. So, say 0, 1, 2, 3, 4, 5. 5 and 0. So this is of type 4. And let's say you have this is type 1. But type 0 is not possible because there are no roots. So we want to consider this type. And then we see if we have this degenerate copy of type 1, 2, 3, 4, and 5. And then we see which one is the largest. And we bound the number of all degenerate copy using that times on number. So we identified the most frequent types of this degenerate copy. And then if you have this, let's say this is the most frequent one, then what does it look like? This look like you have a C2K minus 2 and then 1H here. If you forget this, then this is again homomorphic copy of certain even graph. And instead, now we analyze the number of, homomorphic copy of this. And then shows that, okay, this copy, so before we show that the number of homomorphic 2K copies and most some certain constant times the number of homomorphic copy of this. And then what we show that the number of this is also like certain homomorphic copy of shorter one. And this, this constant multiplied gets larger. And we keep do that. And until we get that these are some K1K. And once we have this, this we can manually count. And then we will get the contradiction because we know the lower bound on the number of copies of J2K. So that's roughly what we will do. So let D of C2KG be the set of all degenerate 2K closed work. Then what? If G has no rainbow 2K cycle, then all homomorphic copy there. Sorry. I was. Yeah, actually, this proof works for some more general rainbow case. I didn't introduce what that means. So, I was getting rid of that concept to simplify it, but I left it for why I wrote there. But anyway, then we know that these two sets are same. Okay, then now we want to show these. So what's our goal? We want to bound the number of homomorphic copies of C2K by some constant times the homomorphic copies of K1K. And that's encapsulated on this lemma. So given a graph G, okay, maybe let's define this one. Let US be the set of closed 2K works that are degenerate at 0, s plus 1. Okay, then what? We have the borrowing inequality. The number of homomorphic copies of C2K in G is at most you consider all of them, and then you measure the ratio between these two. So this is the number of these homomorphic copy. So what's this? This is the number here that we want to find. If we later prove this, then this is exactly this fraction, and that times that to the k times the number of homomorphism from k1k to g. That's exactly what we have here. And then these are multiplied k times. So this is actually here. So that's what I described. And furthermore, we can bound this number by this tool. And we will prove that this divided by u1 is at most 4k squared, some constant number. So here, this number of degenerate copy, and then if we assume that the G has no C2K, then these two are the same. So this gives you this number. So we will prove this lemma. Okay, so how do we prove it? In order to prove this, let's just first prove this claim. So for even S, what can you show? You can bound the size of U sub F by this inequality. In particular, this implies that the U sub 1 are most frequent degenerate copy. We have this. Okay, how do we show this? Essentially, what? You have, what's US? US is that you start at 0, 1, 2, 3, 4, 5, and you come back at F plus 1. And let's come it this way. So this is how it looks like. So this is start from B0, B1, B2, Bs, and then come back at Bs plus 1. So before, I mentioned that one of the advantage of considering homomorphism is that you can use some analytic tool. And what's that analytic tool? Here, I mean, you can do the borrowing. So we want to count all these copies. For that, what we will do is, let's say this is F. So X is same as B0, as well as Bs plus 1. And let's say this is G. So these are chosen. And let's say here, let's say this is Y, which is B S plus K. So from here, this length is K. And then from here, this length is also K. Okay? then the number of these US can be written as summation of all these choices of x, y, g. In addition, what do you have? These two have to be adjacent. And then x and y are arbitrary. And then you count the number of what? I mean, number of homomorphic copies of type 0, s plus 1 with x equal b0 and y equal bx plus k, g equal bs. So you can write it this way. But what can you say now? Here, our trick is you cut this graph in this way. So this part and this part, we treat them separately. What can you write it? This is what? X, Y, G, where xg is an edge. This is summation. And this number of homomorphic copy is what? That's same as the left part. You count the number of the length of here is k minus s, right? K minus s works from y to x. Maybe times number of walks. The s walks from x to g times number of k minus 1 walks from x to y. So that's, you multiply these three numbers and then you add them, you sum them over all choice of x, y, g. Then that's exactly counting this use of x. So you can kind of see now, because this is homomorphism, we don't care whether there is vertices collide or not. Whether this vertex is same with that, we don't care. Then simply you take these two and then you choose any path over, any walk of length k minus x here, and any walk of length s here, any walk of length k minus 1 here, then you find one homomorphic copy counted in US. And then all such copy is counted here. So this is exactly equality. Then what? Here you can apply Cauchy-Schwarz. So you have this times this. Then what does it become? This is Cauchy-Schwarz. For over the same summation, you take the, maybe let me just copy and paste. Sorry. This square times summation of, and maybe let me move it to here. But now these are not arbitrary thing. It has meaning. What's the meaning? So this is what? This is exactly So you have y, x, g, and you take a k minus s walk from x to y, and then you take s walk from x to g, and you square it, meaning that you choose another one, and you choose another one. Then, what's the length of this? This is 2k minus 2s, and this is 2s. So, okay, here you have this. Let me put it here. You add xg is in g in this summation. But even if you forget this, since we are taking on upper bound, you simply deleted it, and this is a bigger one. Okay, maybe, yeah. Then we don't care whether there is an edge or not. Then what's this? This is another degenerate copy with another type. And that type is what? 0,2s. So 0,2s means that the first one is use up 2s plus 1. And what's the second one? Second one is that you take all this x, y, g, and then there is h between x and g and y. You take k minus 1 walk, and then another k minus 1 walk. So that's exactly the homomorphic copy of degeneracy 1, the type 1. So you have this. Yeah, sorry. So when I say the Cauchy-Schwarz, I should have put this. So when you square it, and this is summation of all this multiplication square, then the Cauchy-Schwarz says that this is upper bound. So I should have written this one at the beginning. Yeah. So this is at most this. That's exactly what we wanted to claim here. And then this implies that U1 is the most frequent one. Why? So let's say Uj is the largest set among U1 to UK minus 1. Then what happened? Then Uj is at most, because of this, 2j minus 1 square root of that times U1 to the square root of, U1. But because this is the largest one, this one is smaller than the square root of Uj. Then you have U1. This shows that the square root of size of Uj is at most square root of size of U1. This shows what we want. So this proves the claim. Okay, so you have this one. And then we want to, so this shows that the U1 is the most frequent one. So this first step is proved. And then I want to identify the number going here. That's another step. And then once you do that, and then we want to show that we can repeat this until we bound the number of C2K to here. Okay. Okay. Before doing that, I mean, sometimes, I mean, instead of writing down all these, what you can simply do is the following way. You indicate these vertices that you will fix, and then do the summation of, and then you indicate how you partition it, and then what? And then you squared it. You just draw this. The same as what? By Cauchy-Schwarz, the same as you square this. So this part is squared times this part is squared, and redrawing it, you can draw this way. So this is bounded by this. So this is simple drawing instead of writing down what inequality means. But you can already see what it means, right? So these vertices are the ones that you fix and then take the summation over the choice of them. And then the other parts are indicating that the number of walk time. And yeah, of course, you have to indicate the length of these one. But that's a convenient way of writing it. And let's prove that the 4k square is the right constant that you can take. So what's U1? U1 is the set of degenerate copy of type 1. Then, no, sorry. So let me write it this way. If the number of degenerate copy of type S is, say, at most 2k times US. Let me write it this way. This is what? This is the degenerate type where 0 and 2s plus 1, s plus 1 are identified. So B0 and Bs plus 1. But when you consider the homomorphic copy, B1 and Bs plus 2 same, B2 and Bs plus 3 same, they could also happen, but considering the rotation, the number of those things are all equal. So, I mean, there are 2k different types, all of them have the same type, so this inequality holds. Then what? The number of degenerate copy is what? That's almost 2k times all, you count the all degenerate copy in US, then that's what? That's k of them. And the previous claim says that the U1 are the most frequent one. So this is 4k squared times U1s. So you can prove this. So now we have this first step with the 4k square here. And how do you go down? For that, now you bound this. And then you want to keep bound with in this way, and keep multiply bigger number and bigger number. For that, let's say that that OF be the set of all closed to K walks B0 to B2K with B0 equal B2K such that B0, B2, B2S are all same. So exactly this small big copy of this F of them. So this is our OS. In particular, U1 and O1 are same. Okay, and let's say O0 be the simply any homomorphic copy of G2K. The number of this is F here in this picture. Then what we can prove is the following claim that for S between 0 and K, we have this inequality. So this gives us the bounds between different levels. So you have these different things, and then the previous claim give you the relationship between, three consecutive ones. Using that, we can derive this inequality. Let's say, okay, let's give a name of this star walk of length L is a walk, say, U0, UL of length L, such that every even indexed vertex is the same one. In other words, U0 and U2, you took 2 times floor of L over 2 are the same. So, this could be a star walk ending at here, or this is star walk starting and ending at the same vertex. So depending on the parity of L, it's either closed walk or non-closed walk. Okay, then what? So these are going back, going and coming back, so it's crossing the same edge. So this is OS, right? And how do you do it? Again, you take X, Y, G, and then you want to partition it. You want to cut it. Depending on its parity, you want to cut it in different ways. Let's say S is an even number. 1, let's throw it again. 1, 2, 3. So S is 8. So OS. Then what do? You take X as B0, and then Y is BS plus 1. And then G is BK plus S plus 1. So you have X, and then here, what? Y is B5, right? sorry. Let's say S is 4. 2S is this one, right? 1, 2, 3, 4. So P5. So Y is here. Then what? From Y, 1, 2, 3, and then coming that to G, the length from here to here are K. And then from here to here are again K. Then this number, and then you take its square to apply the Cauchy-Schwarz. By Cauchy-Schwarz, what does it become? This becomes what? You take this is how you cut. You take x, y, g, x, y, g. Then you take the this is length k minus s plus 1, and this is length s plus 1, s minus 1. And then you square it, then sum over all x, y, g, and here x, y are edges. And summation of what? The remaining one. Again, y, x, g, and here y to x, and then go, and then come back, and then here the length k minus s plus 1. Sorry, this is minus 1, and this is s plus 1, and then length here. Sorry, this part is also star work. S plus 1 length star work, and this is s minus 1 length star work. And square. Then if you square it, then what does it become? That's simply, well, this length is 2k minus 2s minus 2, and the length here is 2s plus 2, and that's usually always plus 1. And you sum them up over all. And here again, its length is 2k minus 2s plus 2, and the coming and back here is 2s minus 2 lengths. And this is all, yeah. And if you sum them up over all s, y, g, then that's usually os plus 1, os minus 1. Okay, this is when s was even. And then when it was odd, then it's same. You take x and y, the same number. Instead, you go is 4 times, and then here, and then this is 2 times. And then you do the same thing, and you get the upper bound. So this proves this claim. And then with this claim, what? We can obtain this lemma. Where is the lemma? Yeah. What do you know? You know that the number of homomorphic copy of C2K in G, we divide by U1. It is exactly O0 divided by O1. And from this previous claim, this is what? You can go all the way down to O sub k minus 1 divided by O sub k. But what do we know? If you take O0 divided by OK, then you can write it this way. And because each of them is bounded by this, so this is what? You can write it this way. And what's this? The above one, this is exactly the set of homomorphism from 2k to g. The below one is what? You take a case walk and then, this length is 0. So this is exactly homomorphic copy of k1k in G. And that's exactly bounded by this as we wanted. So that's exactly the what lemma is saying. And then this was already collected. This was the second claim that we proved. Okay, maybe in this claim, instead of this, we just simply write the degenerate copy. Okay, so now we have collected the lemma. We can prove the theorem as we want. So for each k, there is this C such that the extreme number is more C times n to the 1 plus 1 over k. So how do you do it? Let's say large k as 100 times 2 to the k square. Then let's C with 100 k cubed k. K cubed capital K. This is capital K and this is small k. Consider an n vertex C2K free graph G with the number of edges bigger than C times n to the 1 plus 1 over k. Then by the regularization lemma, we can obtain G prime, a subgraph of G on n vertices with what? Its average degree. Let's say D is its average degree. It's at least half times C times m to the 1 over k. And okay, it's 2 over 5 times 5. And what? Its minimum degree and maximum degree. So this is the plus 1 here. Are essentially only multiple consecutive constant k array. In this, if we write it this way, so this is not necessary. Okay, let's write the original one. Then what? The previous lemma. So as the what do we know? is that for this, we prove the lower bound on the number of copies of C2K at the average degree 2D 2K. So that's what? That's 2 over 5 C to the 2K times M squared. You take the 2K power of this. So you get this lower bound. And then now we want to use the previous lemma to bound it. For that, we need to first bound the number of, where is it? 명은? Yeah, number of homomorphism or K1K, number of stars in G. But which can be bounded by using this assumption. This is almost regular, as its degree is almost KD for all vertices in this G prime. You use the convexity of function. This yields that the following. What? You take the all vertices and you take the degree to the k power. That's counting the homomorphic copies of K1K. And this is maximized when? You know the summation, you have a summation of numbers here. Let's say you have x1, x2, x3, x4. And then you know the sum is 100. And then maximum is, say, 50. And when summation of xi to the k maximize, if it's exactly when you have 50, 50, and 0, 0. So the maximum is achieved, and then as much you collected everything to one part, it's maximized. That's because this function is convex. So what? So this is the maximum. And then how many of them can be there? It's many. So this many numbers are k to b. That's possible. Knowing its summation is fixed. Then that's the upper bound. What's that? That's like this times E of G prime. What was E of G prime? That's like maximum degree is this. And number of wedges were these. Oh no, okay. So here, the maximum degree and number of vertices. So this is upper bound. Doing that, now what? The previous lemma states that the number of C2K homomorphism in G prime is what? 2K to the 2K times the homomorphic copy of K1K in G prime. Why? Because of this previous lemma. Because we assume that the graph G does not contain C2K if and these are things. So this is M mod 4K. So 4K to the K, 4K squared to the K is 2K to the 2K. So that's number here, and then you simply write down the other. But what's this? This is exactly this. So you get that if you just plug that in, that's 4k square kd to the km. And you have a lower bound, the 2 over 5c to the 2k m squared is at most 4k square k dm. What do you get? You have m. Here 2k. Here what? nk square k e over c to the 2k. But what was c? C was 100 k cube k. So 100 k cube k is what? You get this. Something is not right. So yeah, this is k. Okay, let me write it again. Yeah, let me rewrite it. So you have this. And what was d? D was this. So that's 4k square k to the k, and d to the k is what? What? 4k square k to the k 2 over 5c to the k m square. And then you delete that, 2 over 5c to the k, 4k square k to the k. So 2 over 5c is at most 4k square capital K. But from our definition of c, it is 40k cube k, lower bound, which is a contradiction. So that means there must be a non-degenerate homomorphic copy of C to K, and it is a contradiction. Okay, so maybe I want to mention one interesting variant of this extremal problem, which is a rainbow extremal problem. So instead of considering graph G, we consider an edge-colored G. And there we say that our subgraph is rainbow if all colors are different. All edges have different color. Each edge gets unique color. And Kibash, Mubai, Stakov, Berstrate in 2007 defined EX tau and H. Is that the maximum number of edges in properly edge colored, which means that no edges with the same color are incident each other, and vertex graph G that contains no rainbow copulates. Then this is called the rainbow Turan number. And then they show that for non-bipartite graph, it is essentially same with the extremal number. Only the lower order term. So Turan density is same if H is not bipartite. And there are questions for the even cycle as well. And Denzer in 2023 showed that this is indeed some constant times n to the, and most constant times n to the 1 over k. And the constant in front, the multiply is exponential in k, and later it's improved to k cube. This is big O k cube. So implicit constant here is polynomial, and that's showed by Kim, Lee, Tran. And which is essentially the proof that I provided before. Although here the constant C is indeed exponential in K, but by not using this regularization, so here we use this regularization lemma. Instead of that, we can just prove that you can find the subgraph, bipartite subgraph, where each part, the vertices in each part are close to each other. The degrees are, it's almost regular on one part, and then the other part also is quite, the distribution of the degrees are quite good. Then, from that, we can also prove a singular lower bound. Then, using that, we can get a pair constant, polynomial constant. But that's essentially, what we did here. Anyway, so this is known. And also another interesting problem is that instead of one graph, you can consider a collection of graphs here. Instead of one cycle, you just put any cycle. And what would it be this? For non-colored version, if you consider the collection of all cycles and then consider the extremal number, then that's n minus 1. As long as you are not 3, you find the cycle. However, here we are considering color. So it may be possible that all the cycles are not rainbow. It's not clear whether this is linear. In fact, Kibash, Mubai, Sudakov, and Berstrade prove that this is at least some constant type n log n. And there was several results improving upper bound, and then the best bound is this is big O n log n times log n. This is by Alon, Uchichi, Zaharov, Dauerman. And in the middle, there was so the proof we did here was upper bound of n log square n. We and Zenzer Sudakov also independently proved this. And by using the above approach, this homomorphism proof, and then take k to be log n, some constant times log n, then you can actually obtain this number by upper bound of n log square n. And then these people further improve this to this almost tight, up to log term, upper bound. And they use something called the sublinear expander theory to obtain this result. Okay, then. So today we proved an upper bound on the extremal number of given cycle. And next time we will learn about some other useful technique. Thank you for listening. I will see you in next video.